Okay, so you are welcome back again. This is part two of numerical analysis or numerical methods. Okay, so the last time we ended at dependent variables, independent variables, parameters, function functions. So without much ado, let's see the meaning of the above. So independent variable is just the characteristics that usually reflects the behavior or a state of the system, right? So for instance, when I write maybe maybe y is equal to mx plus c. When I write y is equal to mx plus c, we know that y is equal to the gradient. Y is what do you call it? The y-intercept, right? That is the dependent variable. It depends on the parameters, right? The parameters here, right? So we have dependent and we have the independent variables. So we have when we move ahead, we see some examples of the dependent variables and independent variables. Okay. So here y becomes our dependent variable because it depends on the other variables in the right hand side for its existence. So that's all about. And the independent variables, example time and space, along which the system behavior is being determined. So it's like, um, for instance, when you have a friend, you see, when you see a friend, sometimes your attitude toward the friend depends on uh, how the person reacts to you. So when you have, for instance, imagine you have two friends and one always the way the person speak, it's annoying. So and the other one, the way the person speak is very nice, it's cool. So among the two, when you meet them, your behavior or your attitude towards them is different because you know that you have met this kind of person, you know that you have met this kind of person, you know that when you meet this kind of person, the way he or she speaks, it's kind of it's not good. So you know how to talk with that person so that he or she will not be offended. The same thing when you see the other guy or the other one who speak normal or who also speak very good. That one too, you know how to speak with. So depending on the independent variables, so the independent variables will determine the behavior of the system. Do you understand? So basically that's all. Then we have the parameters. Parameters are just systems properties, right? They are just systems properties or composition. Then we have forcing functions. Forcing functions are just an external influence acting upon the system. For instance, when a body is, or let's say a diaper, right, is driving, we have some kind of forces acting on. It is an external force or influence, like the gravity. The gravity is acting upon the person. Or when you throw a missile, or when you do some projectile motion, and a body under a projectile motion is being acted upon by some kind of external force, right? So let's see if I think I have some example here. Let's see. We okay. So for instance, this is some example of mathematical model. Then is equal to root gm over cd times of gtd t or over m. Okay, so when we have um, a jumper in a flight, with the jumper is moving with a certain velocity, and that velocity is termed as v. And now here the velocity of the jumper is v. That is the dependent variable. So it depends on the cd. Cd is the drag coefficient. I think it's here, and that is the parameters. Yes, we have the mass and the drag coefficient to be the parameters, and also independent variables. We have the time to be the independent variable, so t is the independent variable, and also I've spoken about the velocity as the dependent variable. The forcing function, as I spoke to you, that is the external influence on the body. And here the external influence on the body is the gravity or the gravitational acceleration. That's what I spoke about. So that's all. Okay, so using the mathematical model stated above, Vt is equal to those equations we just saw, we can perform some computational works on that for the computer to generate at each point in time what will be the velocity of the jumper, right? So the jumper started with 0 time, right? Now the jumper is now at 12 seconds. So at that 12 seconds, from 0 to 12, what will be the velocity, right? So when the jumper started, the time is 0 because the jumper has not moved some distance, and it is assumed that the time is 0 here. And the velocity is also 0 at the initial point. So imagine the jumper started from here, and now you want to travel all the way to this point, all the way to this point. Now, the jumper started here. This is the initial point here. This is the initial point I'm talking about, and now this is the final point. So say for instance, this is 12 seconds. At 12 seconds, the jumper will be there, and now it's the jumper started here 0 seconds. So at each point, so at let's say 6, what will be the velocity? At let's say 8 seconds, what will be the velocity? Let's say at 10 seconds, what will be the velocity, right? So well, you can do some computational work so that you can come out with the values. So we can also use the equation as stated above here. So at t equal to 0, just put t here, and the drag coefficient has been given to us. The drag coefficient has been given to us to be this 0.25 kilograms per meter. Also, the mass of the jumper too has been given to us. The weight of the jumper is 68.1 kilograms. Then also, J is the gravity, which you have to always the gravity should be always 9.81. uh, yes, I encourage you to use that for the computation. And also tange is what do you call it? It's a trigonometric functions. You when you go to the calculator, you can find tange there. Where you click on the shift, I think shift and the high power or something, you will find the tange over there. So when you put in the values, you realize you come out with these velocities. So at t equals 0, you come out with 0 velocity. At t equals 2, you come out with 18.792, and finally at t equal to 12, you come out with some value 50.6175. So you can try that. It's just a matter of substitution. So we realize that this has given us some see, so this is what we term as mathematical model. So upon the situation, looking at the situation, now the jumper is jumping, right? So the jumper is at flight. So looking at some external factors acting upon the jumper, and also some independent and some dependent variables like the time, independent like the time, the man, dependent variables like the velocity. When we are able to come out with this computational modeling or this mathematical modeling, we can determine the velocity of the jumper at every point in time. at every point in time, we can come out with a specific velocity of the jumper. And that is what we term as mathematical modeling. We have to understand the concept of mathematical modeling. Okay, so let's also move on. Let's move on. So there are some things they are not really important. I don't want that. Okay, so let's see some basis of numerical models. So we can also use mathematical models on conservation of masses, conservation of momentum, conservation of charge, conservation of energy. As we can also use perform some mathematical models on that. Okay, so example we have, I think I have this example here. Let me. So in chemical engineering, we can apply these things. We have conservation of mass. We know conservation of mass. Where we have some reactors. So we have reactor one, reactor two, reactor three, reactor four. So these reactors, we can come out with some expression or some model mathematical formulations for that. For instance, with the conservation of mass, mass in is equal to mass out. So mass in is equal to mass out. Mass out. So what do I mean by this? So the mass of the fluid coming in, for instance, when we pick this one, the mass of the fluid coming in should be equal to the mass of the fluid that would leave this container, right? Container one. So that's what I'm talking about. So we have we have a system like this. When we perform that algorithm or when we perform that mathematical models, we can come out with a specific expression. It could be systems, it could be a linear, it could be non-linear systems, depending on the situation. And also, we also have some mass balance here. Normally, these are some mathematical models we can apply, and these are some of the basics applications in numerical methods. In mass balance too, we know that the rate of inputs should be equal to output. That means energy can never be created nor destroyed, right? It can be transformed from one state to another. Yeah, so we want to conserve some energy. The inputs should be equal to the output. So when the output can never exceed, though in some systems, depending on um depending on some external influences and stuff, and even faulty and inefficiency of some machines, the inputs will not be exactly as the output. But we have to assume that in law of mass balance or in law of conservation of energy and mass, the input should be always equal to the output. So we also have some force balances, as in the vertical forces. So when I have this cube here, the force, it is assumed that there's some force acting downward on the particle, and we have some force acting upward on the particle. So the vertical force, upward vertical force should be equal to the the downward vertical force. And also, um, when I have some horizontal force here and some frictional force there, if in case I apply the force in the direction, like the force like in this direction, there will be a friction acting in this opposite direction, right? So you can say the force here should be equal to the force here to keep this body in equilibrium. In equilibrium. So basically, that is um, some things that we need to know. And also in civil engineering too, we have conservation of momentum. So when you have a structure like this, the momentum should be conserved at each point. So basically, that's all. Okay, so we have another one too. In mechanical engineering too, we have machine components. You can also perform some mathematical models on that for conservation of momentum. In electrical engineering, we have so when you have a circuit, um, current at a junction should entering a junction should be called current leaving a junction. You can also apply these conditions there. That is conservation of energy. So basically that's all. You can also have some for loops. Okay, so thank you very much. This end the second section or the second part of the numerical analysis, and I'm hoping forward to seeing you in um, the next video. That will be the part three of numerical methods. And please, if you are new here, kindly subscribe to the YouTube channel so you can get some nice information and adequate teaching on numerical analysis. And not only that, you can get a lot of videos on concerning computations, videos on music or entertainment. Oh, you really enjoy. Kindly subscribe. Thank you very much.